Hi everybody. So today I'm going to be sharing some of my experiences building a web API in Swift to power one of my existing iOS applications. We're going to explore what it takes to build a web service in Swift and how to design and consume an API that can evolve over many years leveraging hypermedia. One of the key parts to successfully rewriting our existing API in Swift was due to an API design we chosen, which was very decoupled from the implementation. API design is very important when it comes to interacting with the web API. Good API design allows us to make huge infrastructure changes and implementation changes without having to change a single line of code in our client-side application. The API design I chose allowed me to entirely rewrite my API in Swift and alter this API design without us updating the client at the same time. So what makes a good API? Well, a good API is decoupled from the implementation details. The API implementation details are not exposed in the interface, and the API should be able to evolve without breaking existing clients. So I'm going to run through a quick example of an API to show how pagination could work and some problems with it. So I'm going to go through a blog API. And the API offers a posts resource, which returns a collection of blog posts. At the start, there were only a few blog posts, and if you was to do a GET request on the /posts resource, it would return every single post. Later on, there were more and more posts, and eventually the API resource contained too many posts for the client to load it in one go. The API had to introduce pagination, so the client could request a subset of all of the posts. Pagination was implemented using page numbers. The page parameter allows us to ask for the posts found on an individual page. And I'm sure you've all seen existing APIs do pagination via page numbers. After you've updated your client to support pagination and then deployed the application to your users, later on you discover a bug in the application, and this is due to how the API was designed. You find a case where if you load a first page and then the underlying content changes, before the client application requests the second page. And when we do request the second page, now one of the posts from page 1 has jumped to the next page, so page 2 now contains an entry that we already seen on page 1. And the client would then have a duplicate post. So how can we solve this problem? Obviously, we could implement deduplication on the client side, but ideally we want to solve this in the API side so each client doesn't need to re-implement these kind of workarounds. And there could also be other problems related to how the pagination worked. So we might decide to drop the concept of pages and instead make pagination work via the IDs of posts. So the ID, or the client knows the last ID of the last post it saw, and it could say, we want to request all of the posts for that specific ID. Now this would solve our problem. And you could say you want to view all of the posts before ID 44, and the server would return a page of posts before ID 44, and the client could take the last ID to use that and get the next page again and again. So how are we going to introduce this change to our API? Many APIs would use versioning to allow these kind of changes. They can keep the existing clients around, the existing versions around so future clients can request the old version. API clients can then migrate to use the newer version of the API and then redeploy the client to the users of that client. We may choose to introduce versioning into our paths, such as suffixing the API path with a v1 or v2. But for our change, this is unnecessary. We don't necessarily need to have the v1 or v2 there because we can alternate the behavior based on the query parameter. Effectively, it is still two versions, though. You still have two code paths, and you still need to support the old version for some time until the clients have been updated to use the new variant. And they've been redeployed to the users, so if a user didn't update to the old version, they're still going to be hitting the old API. And unfortunately, this increases the complexity of our API implementation as we're now supporting multiple behaviors. And our new API design brings along some new problems of its own. We're now exposing implementation details. we're exposing internal IDs of our database and expecting clients to use this information to construct new URLs in our API. The client would be tied to our implementation details. Now, this makes it harder for us to change how the API works in the future. And we want to do so without breaking clients again and again. If we want to move away from our relational database to a new system which doesn't have IDs, then we're going to have to change the data type or such in the URL. And this would break some of the clients. So if the clients were relying on this kind of behavior, they would need to be updated and redeployed. And when you version an API, the version is changed and all of the components or clients written for the prior version will need to be updated or redeployed. Or perhaps they would be abandoned as they cannot adapt to the new API. The other alternative is that we don't change the version and we continue with our current API design that has some of its own flaws because it's not easy for us to update it. And we decide that updating the API to work correctly isn't justifiable, as we have to continue with our current broken API design because it's going to be hard for us to update all the clients or support multiple versions. We could have designed our API in a way that doesn't expose these implementation details. And REST, or representational state transfer, is an architecture pattern that attempts to solve some of these problems. A resource in REST represents all of the current or intended state of that resource, and this would be transferred to the client. The client-represented state may also contain controls that the resource offers and how to transition from one place to the next place in the API. It offers affordances. One of the central themes of REST is to anticipate change and to promote evolvability of clients and servers independently. Both the server and the client should be able to independently evolve without being tied to each other. We should be able to change aspects of our API, like the implementation details and business logic, without having to change our clients. It's common that controls of an API are often baked into the client, and the developer will build an application or API client that's tied to the current knowledge of an API. It's taking design that they've read from the API description and API documentation, and which means that if the API evolves, then some of the clients may be broken and need updating. And to quote Rolf Fielding, the author of the REST dissertation, you can't have evolvability if clients have the controls baked into their design at deployment. Controls have to be learned on the fly, and that's what hypermedia enables. Hypermedia is one of the most important and key constraints of REST, which allows its evolvability. To solve our pagination problem, we could offer clients links to the next and previous states if available. Web linking, or RFC 5988, is a specification for containing links to other resources within HTTP headers. This allows us to introduce link headers to other states in our API. For example, we could request posts, and then it may offer us the next state that we can follow in the form of a link header. If we was to paginate to the last page, the API could stop offering us the next state, as we have no next state to progress. On GitHub, you can find a Swift implementation of web linking. This allows you to pass the link header from an NS URL request relatively easily. So it's a very easy and simple approach you can take. You can attempt to find a link using a relation identifier that you already know, such as next or previous. It is then available. If it's available, then you know that there is this state you can follow. And if there is no state that you can follow, you know there is no next page, so you're likely on the end. You may also introspect all of the available state transitions, which you could use to dynamically place buttons to a user in an application. So if you was to introduce a new feature in the API, it would immediately be available in the application without you changing a line of code. Now, I've shown you a simple way to offer state transitions in HTTP, but there are also other standardized media types that contain state transitions, and HAL is one of these types. In JSON, you may represent a blog post in JSON as follows. We have a title and body, which is the information we're giving to our clients. With HAL, you can provide these links and state transitions that can be performed from this post. For example, I may want to jump to the next post by providing a simple link to it. It is also common to contain a relation to self, which is the current resource. And this allows you to know the canonical URI for the resource and it also helps you to be able to reload it in the future. If my blog started to support comments, I could introduce a transition to the comments. Now a client could follow the transition to view the comments when they are available. Now, what makes How more powerful than web linking is that we can embed other resources directly in the current resource. A How client should attempt to load a transition from the embedded resources section, and if it isn't available, it can then follow a link to the new state. This allows the API to actually embed other resources directly at the current time or possibly in the future. The API may discover that every client always follows a certain pattern. It always requests one thing and then the next thing, and it can observe that behavior and then embed the resource in the future. Or it could perhaps do this dynamically based on some kind of client-based learning. To take this a step further, there is another media type called Siren, which allows you to include more metadata about the transition. It could contain information about the HTTP methods or the attributes that a transition may require. For example, if I am the author of a post, I may be offered a delete affordance so I can delete the contents or delete this post resource. This affordance may not be offered to other users. Since a client will be designed to check if the delete affordance is available before presenting a delete button to the user interface, we are decoupling the business logic on who can delete the post. The client doesn't know the rules behind this, is down to the server. So if it needs to change in the future, the client doesn't have to update. The client becomes a dumb client and it doesn't care about this business logic. If we want to change the logic, so perhaps we want to introduce other members such as moderators who may delete the post, we can do so without updating the client, because the client will just observe if they have the affordance to delete this resource. Siren allows you to represent the transition attributes. For example, we could offer create a comment affordance, which requires the author name and a comment message. A client should be designed to understand these attributes and present them in the user interface. So if one is removed in the future, for example, if you're logged in, then we obviously don't need the author field there. So the client can say, we just want the comment. And the client doesn't care about what it is. It will just render the form that the server told it to. So it doesn't need to know the rule behind logged in users do not see the author field. So to summarize, hypermedia allows us to remove implementation details from our web interface. It allows us to keep our business logic on the back end, and instead of placing this on the front end in our clients. Once we figure out what we're building and some design around it, we can now start building our web service. For me, I already had the design interface settled, although I'm rewriting in Swift. Along with the change of language, I wanted to change some of the implementation details, but I did not want to break the client at the same time, such as how I persisted data. I'm going to cover some of the options and tools that you have for building web services. There is a lot of choice, so it might be difficult for you to start. And of course, you don't have to pick any of these web frameworks. You can, of course, write everything yourself and handle the entire stack yourself. Now, there are there are two popular choices, which is Kitura and Vapor, and this Frank, which is another kind of micro framework that I've been using. So Kitura is a powerful framework which offers many different libraries you can use in conjunction with it, such as database layers. Kitura is an IBM product, so it has a lot of backing and it's likely to stick around for a while. Vapor is another alternative. It has some great documentation, again, has some great libraries you can use with it. And it's gained a lot of traction, and it seems to be a very popular choice. So for my uses, I picked Frank since it's a very small component that only deals with a thin part of the web layer and gives me the control to do whatever I want, however I want to do it. Vapor and Kitura are much larger frameworks that can do a lot more, so definitely worth checking out. Frank is a domain-specific language for quickly writing web applications in Swift. It's a small library which just handles the HTTP routing and leaves other decisions down to yourself. Frank really shows the power and Swift can give you with type safety in the web, which you don't really see in other languages or web frameworks. Now, at the moment, there's a lot changing in the Swift web world. Apple have created a working group, or the Swift team have created it, and a lot of the frameworks are contributing to this, and hopefully in the future we'll have a new standardized way to deal with HTTP in Swift. And existing people such as the IBM Kitura team and Vapor team are all integrating with this. There are a lot of tools you can use to build web services in Swift, and I really don't have time to cover them in this talk. So I'm going to provide you a short list here, which you can take a look later. So there's way more to building a web service in Swift than the code part. And I'm not going to cover the code part in depth, but I'm going to cover the other parts behind it, such as testing it and deploying it and monitoring, as along with the design we already covered. So for testing, you have a couple of options. Obviously, you're probably already familiar with XCTest, the framework used on iOS. You can use it on Linux too. You can write your test just as normally would. You extend XCTest case, class and add test functions. Now, since you're on Linux, there isn't an Objective-C runtime, so that means you have to describe some of the tests yourself so XCTest can run them other than how it would normally by introspecting the runtime. But we can also utilize other HTTP testing tools. There are a wide variety of language-agnostic tools, such as Dread. It's a tool that takes an API description language, such as API Blueprint, and tests your API against it. You can describe your web API in a document decoupled from the implementation. Ideally, you do this before you develop the API, so you know what you're building before you go ahead and do it. And then you can run your tests with Dread against the API description and the URL to your implementation, and it will validate that it matches that. So now you've hopefully built your API, and you've tested it. We should now look at how we can deploy it. So there are a couple of options, and I'm going to cover each of them quite briefly. So personally, I think Heroku is one of the simplest options, since you don't have to worry about maintaining the servers or anything like that. You just push your code, and it deals with all the rest. And it lets you scale up your instances later without any hassle. So to deploy to Heroku, you can use the Swift Package Manager. You just create like a package for your library, mentioning all dependencies. You have your source code, and we have here just it returns hello world or hello username based on the URL. We can specify the Swift version in Swift version file, so when you push to Heroku, it uses the correct version of Swift. And we can build our web app locally and then test it just to see it runs. And when it comes to running on Heroku, you need to tell Heroku how to run your web app. So for this, you have a file called procfile, and you just specify the command line tool that you use to run your web server, which will depend on the web framework you're using, so you can consult their documentation for more information on that. And once we've finished, we can use the Heroku command line tool to build and push our web server. And that's it, it's live. So we've basically done very little, and it's dealt with everything itself. Another option you have is using IBM's Bluemix. It's very similar to Heroku, and it works pretty much the same way because part of it is the fork of the Heroku Swift build pack, so it's a very consistent experience. Obviously, you can also use Docker, but this allows you to run your web service in a contained way, like the same on macOS and Linux. And of course, you can do manually deployment, so you can build your web application and run it on your server just as you normally would. Now, once you've deployed your service, you probably want to deal with monitoring so you can understand any problems that arise in the future. One of the easiest ways to do logging right now is just simply print to the standard out or standard error and observe it. But there are some other frameworks that you can take a look at. So for example, we could just print any errors we hit or whatever, and then we can use some kind of monitoring system such as Papertrail, which would observe the logs, looks for certain criteria, like certain keywords. For example, I could use or configure Papertrail to catch keywords of error and then create an incident in some kind of incident system such as PageDuty. You can also use this to do kind of analytics or statistics where you can print certain keywords and pick them up as events and throw them into a graph. So the most important part of building the API is getting the design right. Once this is tackled, you should be able to easily build your web service in Swift. I've shared with you some popular tools and frameworks that you can use, along with how you can test your web service that you can utilize in language-agnostic ways. I've shown how you can deploy your Swift code to production using the Heroku and other similar tools, along with how you can handle logging and monitoring. Now, there's a lot more to building a web service and programming, so I've covered the basics you need on the whole API lifecycle. And there's another talk tomorrow which will cover the programming part in more depth, which I'd recommend, with a live demo on doing this. So I've covered a lot on this talk, and I've made some resources available at the URL you can see above. You can look at the slides in any link, any like yellow text in the slides you can click to see more information about. Thank you.
Thank you for your presentation. I would like to ask, which web framework would you recommend from your experience?
So as I showed before, there are three that I'd take a look at. So there's Kitura and Vapor. Now, these are pretty big and monolithic libraries, so I personally would prefer Frank. But since I wrote that one myself, I can't really recommend it. But I'd worth checking out all three of them and seeing what works best for your needs, because Kitura and Vapor offer a lot of additional libraries which you can use, such as database layers, and etc. So it's definitely worth checking them out.
はい、お願いします。API ドキュメンテーションのお話が途中で出てきたと思うのですが、サンプルでは API ブループリントが出てきていましたが、他にもいろいろな、スペックがあると思うんですけど、何か比べたりおすすめだったりするのはありますか？
Right, so there are three main contenders in the API description area. So there's API Blueprint I mentioned, and there's also Swagger and RAML. Now, Swagger and RAML are based on YAML itself, so that means they're less readable, which they're often generated from code. So I personally prefer API Blueprint because it's more of a design-first approach, where you go and design your API in a human-readable format, and then later go and implement it. But if you're looking for something to go the other way around, so you already have your API and you want to build documentation on top of it, generated from code, then Swagger's one of the popular choices. And Swagger's also known as Open API now, because they've kind of had a huge push on a new major version. Thanks.
Okay. Thank you, Kai.
Thank you.